Alright, thanks for watching. And in a previous video, I have shown that E is transcendental, which was already pretty crazy. And now you may ask, how do you show that pi is transcendental? And it is even crazier. In fact, it's so crazy, there's some stuff I don't really understand, which I'll skip over, but don't worry, so 80% of the stuff is still cool. Again, I'm not a commutative algebraist, so you literally reach the limit of my knowledge. However, the cool thing is it's sort of based on the same weird trick by taking sums of derivatives. And let's just start again. I wouldn't be surprised if this takes an hour. So now, step one. Again, suppose pi is algebraic. Then what this means, there is a polynomial with rational roots such that pi is a root of that polynomial, and without loss of generality, you can assume the coefficients are integers. Otherwise, just multiply by a huge number to make them integers. So, f of pi equals to 0 for some, again, poly f, with integer coefficients. And it turns out, and you'll see it's pretty cool, we won't really care what pi as much as we'll care about I pi. So notice, if pi were algebraic, then so would be I pi. Is then algebraic. Why? Because consider the following polynomial. So if g, take f, but evaluate this at ix and minus ix. If you consider this polynomial, then let's see what is g of I pi. Well, is f of I times I pi, so f of negative pi times f of pi. But f of pi is 0. So I pi is a root of g. The only problem is, what if g doesn't have, the only problem is g is possibly a complex polynomial. So it's, its coefficients might have i's in them, but it turns out it doesn't, because what happens if you take the conjugate of g? And also, so g of x bar, that's the same as f of ix bar, f of minus ix bar. But because f is a real polynomial, it's enough just to put the bars inside the argument. Yes, I'm putting you behind bars, because this is Payam Police Department. Okay, minus ix bar. You have the right to remain math. Okay, and the conjugate of this is minus ix, and then f of ix. But this is just g, by commutativity. So this is g of x. And so g is indeed a real polynomial, and its coefficients are then integers, because it's just products of integers. And therefore, I pi would be a root of a polynomial with integer coefficients. So I pi would then be algebraic. So it's enough to find a contradiction with the fact that I pi is algebraic. And by the way, yes, there is this other theorem, I think Lindemann-Weierstrass theorem or something, that takes care of this, but I like it raw, like Gordon Ramsay says. So I want a more direct proof. Even though it doesn't make sense, it's nice, because I like direct methods. Okay, so step 2. Again, suppose I pi is algebraic. right? Then I pi is a root of a polynomial of p1 of x. Again, a polynomial with integer coefficients. And the reason I write p1 is because we will use other things like p2 up to pn. In particular, p1 is a polynomial by the fundamental theorem of algebra. It has n roots. So let's call the roots alpha 1 up to alpha n. One of the roots is I pi. Let's just it be the first one. So that alpha 1 be I pi, alpha 2 up to alpha n be the roots of p1. And let's just consider the following expression. It's a weird expression, but well, who says I pi says ei pi, which is -1. So maybe we want to have some expression involving, you know, like ei pi plus 1. And in fact there is. So consider e of alpha 1 plus 1, e of alpha 2 plus 1, dot, 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 e of alpha n plus 1. No, so it's a huge expression involving exponentials, but notice alpha 1 is I pi. So this first term is ei pi plus 1, and that's 0. And so this huge expression, in fact, is 0. On the one hand, it's 0. On the other hand, well, this just looks like it wants to be FOILed out. So let's just FOIL it out and see what monster we created. And let's not do it in generality. Let's just do it for 3, because who says 3 says n. Okay, I say that. Okay, so e of alpha 1 plus 1, e of alpha 2 plus 1, e of alpha 3 plus 1. Notice you'll really have 4 kinds of terms. On the one hand, you have the ones that multiply the exponentials, which are e of alpha 1 plus alpha 2 plus alpha 3. On the other hand, you have terms that involve just 1. What I mean is e of alpha 1 times e of alpha 2 times 1. So e of alpha 1 plus alpha 2. And also, you know, e of alpha 1 times 1 plus alpha 3. So it's e of alpha 1 plus alpha 3. And then 1 times e of alpha 2 times e of alpha 3. So e of alpha 2 plus alpha 3. And then you have the terms that just involve one term. So let's say e of alpha 1 times 1 times 1. Alpha 1. E of 1 times e of alpha 2 times 1. So e of alpha 2. And then e of alpha 3. And lastly, there's a term 1. So 1 times 1 times 1. 1. Okay, and this equals to 0. So ignore the 1 for a second. There are really 3 types of terms. There are terms that just involve 1 alpha 1s. There are terms that involve sum of 2 terms. And there are terms that involve sum of 3 terms. So sum, yeah. So single sums, double sums, triple sums. And in fact, it is the same thing with the, you know, just general term. We would have terms that involve 1 sum, like sum of 1 terms, sum of 2 terms, sum of 3 terms, etc., up to sum of n terms. So plenty and plenty of expressions. And here's the stuff I don't quite get, but anyway. What we want to do, we want to find some huge polynomial whose roots are exactly alpha 1, alpha 2, alpha 3, sums of 2 terms, sums of 3 terms, etc., up to sum of n terms. So I think there's like 2 to the n roots, which are exactly all those terms. So fact 1, well, This I do know because we just constructed at the beginning. There is a polynomial with integer coefficients whose roots are alpha 1 up to alpha n. Okay, that was at the very beginning. But here comes a new thing. Here's where you use some commutative algebra. There is a polynomial P2 with integer coefficients whose roots are all the sum of two terms of the alpha I. So if you want alpha 1 plus alpha 2, alpha 1 plus alpha 3, alpha 1 plus alpha n, and then you start alpha 2 plus alpha 3, up to alpha n minus 1 plus alpha n. Okay. I don't know why, but let me just read this to you. And again, don't ask me to make a video on this because I've been working on this for 5 days and I still don't get it. But it has to do with elementary symmetric functions. So it's because elementary symmetric functions which are basically terms that are symmetric in the alpha i's, something like, I think alpha 1, just the sum of all of them. If you just interchange a couple of the alpha i's, it's okay. Example. So it turns out elementary symmetric functions of the alpha i's, alpha 1 up to alpha n, by some fact in commutative algebra, turns out those symmetric functions are rational. And so are symmetric functions of sum of two terms. The ESF, so elementary symmetric functions of those things. So alpha I plus alpha j. And it turns out because of this fact, one may construct such a polynomial whose roots are exactly those things. Okay. And the cool thing is, it's not the fact that we take sum of two terms, it's not too important because we can also do it with sums of three terms. And also this follows by what's called the fundamental theorem of symmetric polynomials, which again, I'm not too clear about. But okay. So fact 3, there is a polynomial P3 with integer coefficients whose roots are the sum of three terms in increasing order, and in fact, we can do this up to n. So fact n, there exists a polynomial with integer coefficients whose roots are the last term, which is just the sum of all the alpha i's, so n terms. So cool, so there are those n polynomials whose roots are the single terms, the double sums, the triple sums, etc., up to the full sum. And from this, we can actually construct a polynomial whose roots are everything, namely just the product. So if you take the product of those, it solves our problem because it has roots exactly, all the exponents of the expressions from before. So in particular, P1 of x up to Pn of x has precisely roots. Alpha 1 up to alpha n, alpha 1 plus alpha 2, again double sums, n minus 1 plus alpha n, up to the full sum. And again, those are the exponents in the expression star. Sorry that I couldn't give you a more satisfying answer, but I figured I should at least present you something. So, okay. So take it as given, you have this polynomial who has a lot of roots, namely all the possible expressions in the exponential products. Now, of course, some of those things might be zero. So this polynomial could have zero roots, but if it has zero roots, it means it's some expression like x to the blah times something else equals to 0. So if you have a zero root, just cancel it out and just throw them away, and you get a polynomial with non-zero roots. So the point is there is a polynomial, theta x, and let's write it like that just to keep my notation consistent. So c x to the r plus c1 x to the r minus 1 plus blah 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 plus cr equals to 0, whose roots are, let's call them, so instead of alpha 1, etc., call them beta 1. So beta 1, dot, 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 beta r, and then again the non-zero exponents. Non-zero exponents in star. And so in particular, what's nice is with this notation, we can write star in a very easy way. Star then just becomes, instead of saying, alpha 1 plus alpha 2, it just becomes e of beta 1 plus e of beta 2 plus dot 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 plus e of beta r. And remember, there are some zero terms, possibly, but those just become e of 0. So you just add up a bunch of e of zeros, which is just 1. So 1 plus 1 plus 1 plus 1, and let's just say it's k times. K equals to 0. Okay. Where I think k is positive. Yes, it is positive because at least we had this one term at the end. So k is positive. And in fact, if you think about this, I believe k is like n minus r. Possibly not, but I'm just guessing that. Okay, good. So in other words, we took this star, we rewrote this in this form, and we had this polynomial theta, which will be very useful later on. Okay, good. So 1/3 done. All right, and the cool thing is now the rest of the proof, it'll follow just like the proof that E is transcendental. Namely, we want to construct some weird polynomial f, and we're going to take sums of derivatives of terms. So, step 4. Step 4. So, let P be a large prime, to be announced. Now, in fact, we let P like almost go to infinity, just like in the other video, and let S be a huge number, also to be announced. So much, much bigger than P, and in fact, if you want to know it, it's RP minus 1, where R is there, so pretty big. But we'll need that at the end. And let F be the following function. F of x. Okay, it's a kind of crazy monster. So, first of all, remember C, it's the leading coefficient of this theta. So we want C, and for CS majors, you might like that, C to the S. Okay. Then x to the large prime, so p minus 1. And then we want to take this huge polynomial and make it even bigger, theta x to the p. And we want to divide this, just as the other video, by p minus 1 factorial. Okay, so let me erase the other parts. So again, this is also, a Hurwitz type of argument, but it's not clear how it helps us solve the problem, but it helps us solve the problem. And because the sums of derivatives were so fun, we'll do this again. So, and let f of x be, you take f of x plus f prime of x plus dot dot dot, and you take derivatives up to s plus p plus 1. And now, I'm not going to do this again, but remember, the nice thing is there's a relationship between the derivative of capital F and little f. So fact, e of minus x, f of x, prime, that's the same thing as minus e of minus x, f of x. So up to this integrating factor, the derivative of capital F is in fact little f. And now let's just do a little bit of calculus with that. So by the FTC, we get e of minus x, f of x, minus f of 0 is the integral from 0 to x of the derivative of this, which is that. So minus e of minus t, f of t, dt. And now just multiplying it by e of x, what we get is f of x minus e of x, f of 0. It's minus, or maybe let me just write this on a new whiteboard. Sucks, because I might need the definition of little f, but it's okay. Let's just do some calculus first. So, f of x minus e of x, f of 0 is, we have this minus sign, so minus e of x, integral from 0 to x, e of minus t, f of t dt. And as if this is bad enough, we actually want to use another change of variables, and that's maybe to normalize this a little bit. Instead of having from 0 to x, we would like to have something from 0 to 1. So let's just u be t over x. Then, u of 0 equals to 0. U of x, again, let t be x, that's 1. And then du is dt over x. So dt is x du. And so what we're left with is minus e to the x, integral from 0 to 1. So t becomes xu. So e to the minus ux, f of ux. It's almost a bad word, but anyway. And then dt is x du. It's great because this x comes out. Okay. And we're left with, I guess, f of x minus e of x, f of 0 equals to minus x, integral from 0 to 1, e of 1 minus ux, f of ux d. Let's call this double star. Good, that's very good. Alright, so we have this expression here. Again, it's not clear what we want to do, but look, we have this polynomial theta, and we had those roots, beta 1 up to, I think, beta r. What we want to do is plug beta I into this, and just sum over everything. So step 5, plug in beta I into this and sum. So basically we had f of beta 1 minus e to the beta 1 f of 0 plus f of beta 2 minus e of beta 2 f of 0 up to beta r. Which we can just do it directly. So what we end up getting is sum from 1 to r of f of beta I minus f of 0 sum from 1 to r e of beta I. Again, it's just summing up all the f's, summing up the e to the x f of 0, but there's a common factor of f of 0. And on the other hand, we get, I guess, sum of, let's see, minus sum of 1 to r of beta i's integral from 0 to 1 e of 1 minus u beta I f of u beta I du. Okay, here comes a really, really cool thing. Because why did we do that? Well, we have sum of e of beta i's, but remember, this is just the same thing as, right, e of beta 1 plus dot 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 plus e of beta r. And this is, remember why we had those betas? Precisely to have the equation, right, e of beta 1 plus dot 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 plus e of beta r plus d equals to 0. Or sorry, not d. I always think of d, k. Because remember, the beta i's, they're just like the alpha i's and the sums, except they're non-zero. So our original equation with the exponentials was just e of beta 1, etc., plus e of beta r plus k equals to 0. So this huge sum, it's nothing else than minus k. So, what we get sum from 1 to r of f of beta I minus f of 0 times minus k, so plus k f of 0, and that equals to minus sum. There's nothing more we can do here. Sum from 1 to r beta I, sum, an integral from 0 to 1, e of 1 minus u beta I, f of u beta I du. This is wonderful because now we can finally announce our game plan. Here's what we're gonna do. Remember that we have some leeway in choosing p. So p will be a very large prime. So the game plan is, by choosing p very large, we'll make the left-hand side a non-zero integer. On the other hand, we'll make the right-hand side less than 1. And that would be a contradiction because there is no integer that's non-zero, but also very small, in absolute value. And so we will deal with two things, first with the left-hand side and then with the right-hand side. So, step 6. So left-hand side, what was it? It was the sum from 1 to r of f of beta 1, beta I, and then plus kf of 0. Great, but now let's actually use the definition of our capital F's. Recall that capital F was just a sum of a bunch of derivatives. So maybe recall capital F of x, that's just f of x plus f prime of x plus dot 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 plus f of, again, up to s plus p of x. And let's see, maybe a different start, but now we want to separate it into a bunch of cases. One where we take few derivatives, and one where we take lots of derivatives, just as before. So, case one. Suppose you take just a couple of derivatives. Suppose m, which is the number of derivatives, is not very big. I'm claiming that, in fact, in that case, the sum of little f's is small. Fm of beta, I guess, beta I, equals to 0. And this just follows from the definition of f, because, look, remember that f of x was c of s, x to the p minus 1, theta of x to the p over p minus 1 factorial. Ignore this, ignore like everything here. It follows because, look, p in this case is a huge power. So let's say, first of all, you don't take any derivatives. If you plug in beta I, remember beta I was the root of theta. So theta beta I is 0. In particular, f of beta I is 0. So no derivative is fine. Let's say you take one derivative. Okay, by the Chen Lu, it would be p theta p minus 1 times theta prime. You would still have a theta to the p minus 1. And if you plug in beta I, you still have 0. And same thing happens whenever you take derivatives less than p. So, because each term then becomes 0, the whole sum is 0. So that's good. That's if you take a few derivatives. Now let's see what happens when you take more derivatives. So case 2. So m greater or equal to p. So huge number of derivatives. But remember, we're also taking less than s plus p derivatives. Then again, let's just expand f out. So the point is, let me see. All right, and we get, yes. Then again, use the Chen Lu. If you take more than p derivatives, then here's what happens. So remember, we want to evaluate the derivatives at beta I. So if you take all your derivatives here, you would still get that this is 0. So because we still have a theta x that appears somewhere. So suppose worst case scenario, you put all your derivatives, or at least p derivatives, on here. Then you're still safe, because what happens is that you would still have, your constant c of s, and then p minus 1 factorial, and then x to the something. So even if you take some derivatives here, it's fine. But if you take at least p derivatives here, then you have some p factorial coming out. And that's just by using the Chen Lu a bunch of times. So you have p factorial times some huge expression. And that's good because what we're left with then, the p factorial and the p minus 1 factorial cancel out, and you get pcs x to the blah times blah. And what's important is that this sort of becomes a polynomial, more or less, but whose coefficients are divisible by p. So not only that, divisible by pc to the s. pc to the s. And so this is, next argument is slightly hand-wavy, but what happens then is that even if those terms are not necessarily 0, if you plug in beta I into those things, so fm beta I, what this becomes then, it's a polynomial in all the betas, remember, because we had our theta, which involves all the betas, so beta 1 up to beta r, of degree at most s, because I think at the beginning we had sort of s plus p roots, but we're taking at least p derivatives. So this makes the roots, like the degree, go down by p. And each coefficient is divisible by p to c to the s. Is divisible by pc to the s. And you may ask, why is that important? I don't know. That's again the limit of my knowledge, but let me tell you, at least in words, why, what happens there. Because here's not important is the fact that we're playing with sums. So in particular, suppose you take the whole sum, I from 1 to r, f to the m, the mth derivative of beta I. Notice, this whole sum is symmetric. If you interchange, let's say, beta 1 and beta 3, the whole sum it still stays the same. So it's symmetric in beta I. In beta I. And so there's this theorem called the fundamental theorem of symmetric polynomials, which again I have no idea what that is. So I looked at it and I was still confused. So by the fundamental theorem of symmetric functions or symmetric polynomials, and the fact, this it turns out is very important, and because the coefficients are divisible by c to the s, are divisible by c to the s, it follows, and again it's pretty surprising, so because of this symmetry assumption and this divisibility assumption, it turns out this whole expression is an integer. Very surprising, even though we had this p minus 1 factorial. That the sum I from 1 to r, fm beta I, is an integer. It's kind of cool. So in both cases, we actually have an integer. Because in the case where m is small, all the terms are 0. In the case where m is large, by this fundamental theorem, it's still, it's still an integer. Okay, good. And not only that, it's an integer, but because it's divisible, each term is divisible by p, it's actually p times an integer. So, okay, I think it was the last thing I didn't understand. So from now on, I actually know the end. So, and we're at like the last third. So. So what we have then, the sum from 1 to r of fm beta I equals to, again, p times an integer, so p, let's call it km, where m, again, is big, so it's from p p plus 1 up to p plus s. So for small m, and for large m, it's an integer. For small m, it's 0. And then, in particular, I think I'm going to skip that calculation, but the left-hand side, that's the sum from I from 1 to r of capital F of beta I plus kf of 0. Okay. And remember, capital F is just the sum of the derivatives. So capital F is just the sum, I guess, from f of m, but this sum m from 0 to, I guess, r plus, p plus s. Let me just, yeah. So if you just replace f by the sum and you interchange, the summation, it turns out at the end, you just have p times the sum of km, and just from m from p to s plus p, km. Because all the other terms are 0, and remember you still have the term kf of 0. So that's great. The left-hand side, at least this term here, it's an integer. And now what we want to show in the next step, we want to show that this is also an integer. And here again, we want to use the specific form of little f. Okay. So left-hand side is almost an integer once we show this. And remember, the goal is to show that the right-hand side is small. So, step 7. So kf0, almost like KFC, but with a 0. Now, remember, as before, little f is c to the s, x to the p minus 1, theta of x to the p over p minus 1 factorial. And what is f of 0? Capital F of 0 is just the sums of derivatives of f at 0. And we want to use an argument very similar that E is transcendental. So case 1, again, suppose you don't take many derivatives. So suppose you take up to p minus 2 derivatives. Interestingly, before it was the term theta that was important, now it's the term p minus 1 here that's important. Because look, what happens if you plug in 0? Well, you get 0 to the p minus 1. So f of 0 is 0. And if you take the derivative, well, worst case scenario, you get p minus 1, x to the p minus 2. And if the derivative, if p is large, that's still 0. And it turns out you can apply this whole argument up to the nth derivative is p minus 2 equals to 0. So if m is small, the nth derivative is small. Let's see what happens to the border case, and that's kind of interesting. Okay. Now again, worst case scenario, all the derivatives, they fall on the x. If even one derivative falls on here, we're still saved because we have 0 to the something. So, worst case scenario, we have something like that, where we have c to the s, p minus 1 factorial, and all the derivatives fall on here, which would result in a p minus 1 factorial. And everything else is here, theta 0 to the p. And this cancels out. And I like to remind you that, theta of x, I think was like c, let me double check. c times what? Yeah, cx to the r plus blah 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 plus cr. In particular, if you plug in x equals to 0, you're just left with cr. So cs and then cr to the p. And this will be important because you'll see it shows that it's like not divisible by p, which we need that. Okay. That's one thing. And then lastly, what happens if we take lots of derivatives? So in case 3, what if m is greater or equal to p? Well, greater or equal to p but less than p plus s. Then again, worst case scenario is if all the derivatives fall on here. So, or I guess if at least p minus 1 derivatives fall on here. So what happens is that we get c to the s. Again, possibly some x's here, but forget about that. Now, suppose you take p derivatives here, then we have at least p times p, like p factorial, times p minus 1 factorial, times higher terms, times some derivatives of theta, which again doesn't matter here, and we divide this by p minus 1 factorial. This cancels out, and the point is, we're left with p times an integer. We don't need f anymore right now. The point is, we have p times blah. In fact, this blah, let's call it km. I guess capital Km. The point is, if you take a huge number of derivatives, not only is it an integer, you actually have a number divisible by p. So it turns out then, if you take the sum of them, we get 0 plus something, we'll see that's not divisible by p, and a number divisible by p. So again, so in fact, kf of 0, that's just a bunch of zeros, 0 plus 0 plus cs, cr to the p, plus, I guess, p, we had the k, so pk, and then sum of km's, m from p to p plus s, and that's an index. Okay, excellent. So in the end, just to summarize, we have this thing. Let's remove the zeros. So kf0. I forgot. We also have k. So this is kf0 in particular. What happens to the left-hand side? So summary. Left-hand side, we got, first of all, I think the sum of f of beta i's, so which became p times sum of m from p to p plus s, little k of m, plus k c to the s, cr to the p, and plus pk, sum m from p to p plus s, capital Km. So the point is, what's nice about this is we have lots of multiples of p and this other term. So what we really have is blah times p plus k c to the s, cr to the p. Let me now remind you what all the terms are. K, remember it came from this e of alpha 1 plus alpha 2 plus alpha 3 plus dot 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 plus e of 0, which is 1. Remember we said there might be some 0 roots, and let's just delete all the 0 roots, and we get those beta i's, except we have a bunch of terms that are e of 0 plus e of 0 plus e of 0, and those terms we just call it k. So we add something like e of beta I plus k equals to 0. And because there was at least one term, k has to be non-zero. This has to be non-zero. Now, c of s, c, what was it? It was the leading term in theta. Right? Theta of x was cx, I think, to the r. And let me double check this just to make sure. Yeah, c of x to the r plus dot 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 plus cr. Now, well, c is the leading term, so for sure it's non-zero. Otherwise, we would have the 0 polynomial. And lastly, cr, that's also, what do you want to say? Cr, it's also non-zero because look, if it were 0, theta, it would have a root of 0. But we chose those beta i's precisely to have non-zero roots. So this whole thing is non-zero. Okay. All right, so the point is we have blah times p plus some non-zero integer. And here's the cool thing. Remember, all those terms, they just depended on theta in our original expansion. They didn't really depend on p, okay? Except maybe this exponent, but you'll see it doesn't matter. So what we want to do, and it's really cool, we want to choose p large enough, again, p is a prime, right? We want to choose p large enough such that this is not divisible by p. So in fact, choose p large enough such that this is greater than p. Large enough such that this is not divisible by p. In other words, what you could do, just choose p to be like the next prime number that's smaller than that. For example, if this is 17, no, even that better. If this is 18, just choose p to be 19. Because it's a prime number bigger than that, this is definitely not divisible by p. So that's the cool thing. And I know this is factor of p, but trust me, one can do this by choosing p large enough. All right, so in particular, because this is not divisible by p, this is of the form, mp plus something not divisible by p, so mp plus r. So where r is positive, and so because this is not divisible by p, it turns out this whole thing, it's non-zero. I know. All this work to show something is non-zero, but yes, it is a non-zero integer. And now all we want to do, we want to show that the right-hand side is very small. That would be enough to conclude. So, last step, oh my god. It's like in Super Mario, you're at the 8th castle. So this is step 8. So right-hand side. But the cool thing is, this has integrals, it's back to calculus. Again, no weird number theory. So the right-hand side was the sum from 1 to r of beta I, integral from 0 to 1, e of 1 minus u beta I, f of u beta I du. And now we want to use the form of f. So the definition of f. So this is minus sum from 1 to r of beta I, again, integral from 0 to 1, a of 1 minus u, beta I, okay, again, cs, u, again, u beta I, so u to the p minus 1, beta I to the p minus 1 over p minus 1 factorial, and then theta u beta I to the p du. Again, f is just cs x to the p minus 1 over p minus 1 factorial, theta x to the p. So just use f of u beta I. And the nice thing is, those beta i's, they like fuse together. So this comes in here to become beta I to the p. And not only that, yeah, sure. Not only that, here comes the cool thing. So far, we haven't chosen s yet. Remember, s was just still here. Now we want to choose s. So now let there be light. So let s be rp minus 1. What happens here then, we get c to the rp minus 1, which this minus 1, if you want, comes outside. So it becomes minus sum from 1 to r, 1 over c, integral from 0 to 1. Okay, now, u to the p plus 1, let's put it here. I know it's a bit messy. E of 1 minus u beta I. Beta I times beta I to the p minus 1. It's beta I to the p. So let's actually put a huge thing. So beta I to the p, theta u beta I also comes in with the power of p. And now look, we had this crp minus 1. This minus 1 came here, and this just becomes c to the r to the pth power. So we have a big thing, it looks like Krabby, cr beta I, and of course divided by p minus 1 factorial du. Okay, so we have that. I know, super, super messy, but it turns out this becomes actually easy to estimate. So let's estimate this term now. Because now let's see what happens to absolute value of the right-hand side. And remember, like most of the terms are sort of between 0 and 1. Like u is between 0 and 1, which makes it very nice. So, right-hand side is less than or equal to, again, absolute value, this minus becomes plus, use the triangle inequality and put it inside. Sum from 1 to r of, I forgot if it's positive or not, but let's just put 1 over absolute value of c. We do know it's non-zero, so we're good. And then again, triangle inequality, put this u to the p minus 1 in absolute values, and then also e of 1 minus u beta I. Okay, and again, other terms, we'll talk about this in a second. Well, u is between 0 and 1. So this whole thing is less or equal to 1. And also, again, 1 minus u is between 0 and 1, and beta I, they're fixed. So it turns out this is also less or equal to some constant, because again, they're just finite many of the beta i's. And we're left with this thing. So c to the r beta I, theta u of beta I to the p over p minus 1 factorial, again du. And my claim is this actually goes to 0 as p goes to infinity. It goes goes to 0 as p goes to infinity. And it's a similar argument to what I did with transcendence of E. But it's so much fun, let's do it again. So let's call this, I guess in this case, AP. And then let's just calculate, again, maybe absolute value, that's fine. So AP plus 1 over AP, well, that's CR beta I, theta U beta I, to the P plus 1 over P factorial, again, cross multiply. Okay, and then P minus 1 factorial, CR beta I, theta U beta I, to the P. Everything, most things cancel out, so this P cancels out with this P here. This cancels out except with a P. And you're left with CR beta I, theta U beta I, over P. And the point is, this goes to 0 as P goes to infinity. In particular, you can make this less than 1/2. And therefore, by the ratio test, the series of APs converges. And so by the divergence test, we need to have that AP goes to 0 as P goes to infinity. But again, we don't want it to go to 0. I mean, we don't want P literally to go to infinity. The point is, you just choose P to be very large to make this very small. And so what you're left with is just some small term times a constant times sums of terms. And so, to conclude, what we're left with is this is less than or equal to sum from 1 to r of 1 over c, integral from 0 to 1, c prime times small, du. And the point is, this is small. So, super rigorous math, okay? So this is small if P is large enough. Okay, and now let's just quickly conclude. What do we have? So, we have that the left-hand side equals to the right-hand side. We know that the left-hand side is an integer, not divisible by P. Right? But what we've shown now is basically the absolute value of the left-hand side equals to the absolute value of the right-hand side, which is small. So you can make this less than 1, but an integer whose absolute value is less than 1 has to be 0. So the left-hand side equals to 0. But on one hand, on the left-hand side of the left-hand side, it's not divisible by P, but P does divide 0, and that's a contradiction. And therefore, contradiction with the fact that pi is algebraic, and therefore pi is transcendental. And then we're done. And remember, I sweep some things under the rug. So imagine how long that would have been. But yes, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.